Welcome back, guys. In this video we're going to solve two short problems, one about the linear impulse momentum and the second one about the impact of system of particles. Now if I take a look to this example here, I have a tank car that has a mass of 20 megagrams and it's freely rolling. Freely rolling means it doesn't have any frictional force, right? And it doesn't have any other force. In fact, it's free to roll to the right with a speed of 0.75 meters per second. If it strikes this barrier, determine this one here. I need to determine the horizontal impulse needed to stop the car if the spring in this bumper B has a stiffness of K that is going to infinity and K here that is going to 15 kilonewton per meter. You're gonna see, guys, that this K doesn't affect the answer of this horizontal impulse needed to stop the car, because in fact I know that so I know that mv1 plus the sum of all the forces dt, this is the linear impulse, is equal to mv2. I'm gonna take this tank car as my free body diagram. Now, just before the impact here, and just before stopping the car, what are the forces exerted on this tank car? In fact, there is only one force, which is the impulse of this spring force. All right, so there is only one force, which is the force in this bumper at B. Okay, so what I'm gonna do now is to, of course, cancel out this mv2, so this will be equal to 0, and now mv1 will be equal to 20 times 10 to the power 3, because this is in megagrams, times 0.75, which is the velocity of this tank car, plus I, so I'm gonna call it as I, is equal to 0. Now this means that this I will be equal to minus 15, and then minus 15 means it's in fact in the negative direction of the motion. So this is x, then this is the force of the spring in the bumper B. Alright, so now this means that the impulse of this force is equal to minus 15. In absolute value, the impulse of this force is equal to 15. And what does this mean in terms of K? I know that the force inside the spring is K times S, and I know that the impulse is the force, which is K times S, times what? Times delta T. Alright, so I'm gonna say it's the force inside the spring. Of course, now here it's the integration, in fact, because S could not be constant. Alright, so times d, so let's do it like this, times dt. Alright, and I know that inside this force of the spring I have k as dt. Alright, and in both cases, whatever is k, this I should be equal to 15. It's constant from this equation. Right, now if k goes to infinity, then dt or delta t or t, the time needed, or the period of time where this impulse occurs, should goes to 0. Alright, because in fact it's 15 over a certain number that is going to infinity. Alright, so if k goes to infinity, then of course dt or delta t or the time should be going to 0. Now if not, if k is going to 15, then of course I should have more information about S in order to do the integration, but I am sure that the time will be greater than this time that goes to infinity. So then the time where k goes to infinity. All right. So you can think about example 2 as some concept. In fact, we cannot find the number. Right. Now, let's do example 3, which is about the system of particles, and in fact, it's very easy. So take a look on this example. In fact, here, I have a bus, B, that is traveling to the right at 20 meters per second. Meanwhile, I have a car, A, that has a mass of 2 megagrams, and it's traveling also at 15 meters per second to the right. So now we're gonna have an accident. So these vehicles will crash, all right, and become entangled. What does this mean? Entangled means they will stick together as if they are the same body. I need to determine their common velocity just after the collision, and take a look, guys, on the sentence. It's a very important sentence. Assume that these two vehicles are free to roll during collision. So during collision, guys, they are free to roll, which means during collision, there is no forces, which means during collision, the impulse is equal to 0, right? So they are free to roll. So that's why I'm gonna say that the momentum just before collision plus the linear impulse that is equal to 0 should be equal to the momentum after collision. Now, what is the momentum before collision? It's MA VA plus MB VB. Why? Because they are two separate bodies, alright? Plus the linear impulse, which is equal to 0, because in fact there are no forces, and this is the question. They are saying that I have to assume that the vehicles are free to roll during collision, so there is no forces in x direction. Of course, there is a force in y direction, which is the weight and the normal force, but in x, so these two velocities are in x, there is no forces during collision, and this will be equal to the momentum at state 2, which is here, will be the state just after the collision. And I know that just after the collision, they are entangled, which means they are one body. What does this mean? One body means they have the same velocity. So I have only one system, and the system has one velocity, which is v. Right, so I'm gonna say ma plus mb times 1 velocity, which is v. Alright? This is the common velocity that I need to determine just after the collision. Okay? So if you substitute each term by its value, you're gonna have that v is equal to 18 plus 57, and of course it's in the positive direction. So 18.57 meters per second. So guys, after collision, if this is the bus and this is the car, they will be entangled and they will roll together with this velocity that is equal to 18.57. Thank you.